So the first two lectures on the theory sections which we covered is basically the general know-how about GPS in terms of the coordinate system as well as the signals. So today we are a little more going to the mathematical manners, how to use those information, and what if you have to do a little coding and you have to do little processing on your own without taking help from certain softwares. So that how would you start? So this will help you in understanding certain mathematical background also, but obviously this will take a little more understanding of the mathematics which you know. So okay, so yesterday we discussed about two ways where we can develop our observables so that that could be used for processing. So we started with the code pseudo ranges, that is measured with the help of PRN codes which are modulated onto the carriers. One is CA code, another is P code. So if we are using codes and we are measuring this time shift, then the observable which we came across is, we call it code pseudo ranges. So one, we'll discuss the model about code pseudo ranges also. Second, what if we are using the carrier phases directly, because as I said, the measurement of carrier phase is actually helping us to achieve the millimeter level accuracy, isn't it? So both are actually relevant and they both complement each other also. So we'll see the mathematical background of the code pseudo ranges as well as for carrier phase. Then why we go for a different ways of measurement strategies, that will also be discussed. So we'll start with the point positioning. Simply you have a receiver and you want the point position using with the help of the data acquired. So we'll see the point positioning using code ranges, code pseudo ranges I would say, and the point positioning using carrier phase. So another point is we actually evolved during when the selective availability was available, is that how do you start this which we call it differential positioning, or we call it DGPS. So evolution of DGPS started when the selective availability was there, and nowadays it is helping us to achieve little more accurate information with the help of code pseudo ranges. We'll discuss about this also, what do we mean by differential positioning, and we'll see about the relative positioning also. We'll see the difference in the nomenclature, why we call it relative, why we call it a differential, isn't it? So in the relative positioning also we'll go for static relative positioning, and we'll see what do we mean by kinematic relative positioning. So the nomenclature itself, it's very straightforward, and you could also understand when we are talking about the point, it means we are sticking to a point information. When we are saying the kinematic, eventually you could also relate that it is in motion. Something is in motion and you want to track of this motion. Then obviously, since this point positioning can be in static manner and can be in kinematic manner. So we'll see that these different, and also we'll have a complete altogether lectures on the different strategy of the measurement strategy, which we also call it surveying ways or GPS surveying ways, where we can use the GPS for different type of measurements. So we'll see that also in a different lecture, but today we'll cover those which are more relevant to your understanding. Okay, so yesterday we discussed that we have a time system which is more relevant to the GPS time. We are actually working in this GPS time, and in order to understand the mathematical model of code pseudo ranges, we have to understand that this is actually we are measuring, which we call it delta t, and delta t is nothing but the difference at the stamping or the time tagging at the moment it transmitted the signal and the receiver received it. But as I said, both end, not only at the receiver end but at the satellite end also, the clock errors happens. But since satellite is more intelligent, it is telling you that how could you estimate those errors. So that's why we don't take into the account the satellite clock corrections as an estimate, okay, or as an unknown. So what we'll do here, we'll try to see how this delta t could be represented so that it makes sense. So the Tj, the the upper script Z is satellite clock time at signal emission, that is the time tagging. Offset, it has offset from actual GPS time because of the drifts which are occurring at the satellite. Then TI, which we call it receiver clock time at signal reception, and that also has certain offset from actual GPS time. Similarly, delta J, which we call it satellite clock delay with respect to GPS time, delta I, which we call it receiver clock delay with respect to GPS time. So we'll try to see how these two are related so that we could actually, and what if these delays were not there on both ends, what will happen? So this is TJ star, which we call it satellite clock time at signal emission in GPS time frame, and simply TI star, which we call it receiver clock time at signal reception, both in GPS time frame. So we'll try to see what if those errors were not there, how would you write it? So delta T is nothing but the actual signal emission time, signal reception time, and we actually are estimating these individual time, or we are trying to relate this in with reference to this GPS frame time, is that TI is nothing but the actual time of reception in GPS time frame plus those offset. Similarly, for satellite end also we have TJ star plus those offsets. So both offsets are available with respect to the GPS time. So that is actually quite straightforward. Second is, we are actually, as I said, it is the delta T which we are actually measuring at the receiver end. So it is the same equations, and this is the actual what we call it, if there is no error, this is the actual time difference between emission and reception in the GPS time frame, but this is the actual, the call it satellite receiver clock offset, isn't it? So TI star minus TJ star would become the actual time of travel in the GPS time frame plus those clock correction. So we call it pseudo range because it is not the actual one, instead it is slightly shifted from those actual geometric range. So we call it pseudo range, which is nothing but the C delta T. C delta T would eventually become C, this equation C delta T would become C into this, and C this part with the time offset in the GPS time frame plus those offset in the clock offset. So this eventually become this term, which is actual, there is no offset, is become geometric range, and this P minus this C delta. So I am telling this in detail for those who don't have much background on the understanding about this pseudo range measurement. So similarly, we have this pseudo range measurement. This you could relate with your lecture notes. Pseudo range between ith receiver and jth satellite. So this is a proper notation which you have to follow, or when you are reading certain books on GPS, you have to follow this kind of notation, that when you write pseudo ranges, you have to write between which receiver and which satellite you are measuring. So that will automatically become more helpful for writing or understanding those equations written in the literature. So it is nothing but the true range or geometric range plus those offset. And as I said, we know somehow our satellite tells us about that the clock offset in their in their clock, so that we actually have this estimate of which we call it satellite clock offset from the GPS time, and those parameters are given in the navigation message A0, A1, A2, and you try to estimate those corrections. So Pij, and on the left hand side we have complete, which we call it observables, and on the second hand side we'll see how this rho ij is actually written. So it is nothing but your 11th level mathematics, you could write the equation, distance equation between 2 points if you know the coordinates, and we know the coordinates of the satellite. Please remember it, isn't it? Because not directly, but we have to measure it, or we have to estimate the coordinates from those parameters. So the xj, yj and zj, or which we call it the position of the satellite in a certain reference frame, we know it or we measure it. So this geometric range, which is written as with respect to this ith receiver and jth satellite, this could be written in this manner, and it is nothing but is a function of xi, yi, zi, which is nothing but the position of your receiver. So eventually you are interested in finding out this so-called position of your point, isn't it? So you have got a function which is related with a function of xi, yi and zi. We'll see how it can be used for actually estimating those xy. So With respect to the initial approximate coordinates, so those who are understanding the more of the gamut, so you have this a priori coordinates which is with respect to which you are actually estimating or trying to see the variations in the final estimates. So we'll say we have initial coordinates of this receiver point or the station xi naught, y naught, z naught. So simply we have to estimate this little shift from that initial position so that we could estimate our receiver position. So this is nothing but using Taylor series expansion for linearization. We are not considering the higher order term here. So f function of those receiver xi, yi, zi will start writing the with respect to the initial point, the function value, partial differentiation with respect to x, y and z, because these are varying term, isn't it? So it is nothing but this delta x is nothing but xi minus with respect to that initial coordinate. So delta x, delta y, delta z. So this is little straightforward. You could see just a moment this equation because we are using this equation throughout in this GPS, isn't it? It is nothing but the linearization of the function which is this, and we are writing in a proper sense. So that could make a proper sense to your understanding. So this partial differentiation, if you could partially derivate this particular distance equation, is nothing but straightforward. 1 by 2, this automatically comes in the bottom, and then partial differentiation of this particular with respect to x, this 2 becomes 0. So it's very straightforward. This is the component which you could see over these places. I hope all are relating with this. Okay. So again, we'll come back to that our original equations for this. This is nothing but the true geometric range rho ijt, which is nothing but again this term, and rho ijt naught with respect to that initial coordinate minus individual putting those components here. You will see this a very nice equation written for those this particular term. Okay. So as I said, rho ijt naught is nothing but the so-called we are taking the vector difference between these two. So this eventually become straightforward equation for this component. We again rewrite those equations, pseudo range measurement between ith and jth, rho ij naught, rho ijt with at epoch t. Eventually, because at every epoch we are getting the measurement from the satellite. If you see the Rhinex file, for every epoch you have certain measurement from those particular satellites in terms of pseudo ranges, code pseudo ranges, as well as for the carrier phase measurements. So this we are putting this value here of from the previous slide. This is a little straightforward. Then the receiver clock offset, satellite clock offset. So this term eventually we know from the navigation message. With the help of navigation message, this eventually becomes your prime observable, isn't it? So this is nothing but the pseudo range, the initial approximation with respect to the initial coordinate, and then the c rho jt, which is the clock offset from the GPS time. So this is nothing but which we write as the L. Now I'll come back to the second part also. What we are using here, why we are making these notations, is that the prime observable L, which is nothing but the pseudo range and the initial distance measurement with respect to the a priori coordinates, which you call it, and the clock offset measured from the satellite end. You could write this, you could form these equations. So now you could see I am changing these j from 1 to 4. You could see j is equal to 1, 2, 3, 4. What it is doing, it is actually taking the similar measurements from 4 different satellites, so that you could have unknowns, understanding 1 unknown, 2 unknown, 3 unknown and 4 unknown. So you have 4 unknown. For a unique solution you need to have at least 4 observations. So that's why we are taking measurements from 1, 2, 3, 4. Those who don't have much understanding about the satellite geometry, which we will cover on the next lecture, someone could say that what if we could take T1, T2, T3, T4, because for 4 epoch we will also have this measurements. So we'll see that why can we, it is not favorable to do it, isn't it? We'll see that part also. Okay, so this equation, similarly, if we use the matrix notation to write this equation, the complete equation, so you could see that the parameters or unknowns are these 4 terms which are similar in every equation. So similarly we could write A as, which we call it design matrix, Those who are little understanding about the least square estimates or the process of least squares, so they would see that the design matrix, the role of design matrix, the unknowns, the prime observables, and you would have V is equal to AX minus L. Okay, so this is nothing but the observations, which we call it raw observables here, the unknowns, which we have the 4 unknowns, and that's why for a unique solution, in the first slide yesterday we have said for the GPS position you have not only 3D position as well as you have receiver clock offset also, so that becomes a 4D problem. So this V is equal to AX minus L, you have to solve based on the number of observations available, you have to solve for those X, and that's how you get the position estimates for your receiver. Similarly, it is just one step, we have to move for the model, understanding the model for carrier phase also, because we are not only using the codes, we are using the carrier phases also, and eventually the carrier phases are the one which we take so many uses in the terms of those observations, L1, L2. So we'll see how the equations for carrier phase are written, and please remember that we have skipped those error term here. Obviously they are there, but for more understanding of their mathematical model, we have assumed that at this particular time we don't have any those errors. Okay, so assumption is similarly here, we are not considering the error term, which is atmospheric as well as the hardware delay. So this is the very straightforward equations, which is nothing but relating the lambda multiplied with this phi obviously makes is that it becomes in unit is meter, isn't it? Where lambda is the wavelength of that particular carrier. So if you are using L1, you have to put the lambda 1. If you are using L2, you have to put the lambda 2. And similar equation is this. This last term, which we call it ambiguity, we have to resolve it to get a solution for our position. And the term which N is that the moment you get locked, it becomes constant. You have this doesn't vary until unless you don't lose the lock. So this rho ij plus c, again the similar term, we don't explain it here, the similar term, plus those lambda n ij, this is an additional estimate, or you could say additional parameter, I would say. So lambda phi ij would write the equation similar to the previous explanation of Taylor series expansion, will not repeat it here. So this second portion would automatically becomes clear to you. Then we have again the receiver clock offset, satellite clock offset, as well as this ambiguity term. So this equation is written for the units in meters. So your L becomes nothing but similarly to the previous one, the L and the prime component of the so-called design matrix could be clearly explained. So this eventually here you have delta X, delta Y, delta Z of your receiver, the clock offset, as well as this ambiguity term. So you could see, since you are locked to not only one satellite, instead more than one satellite, you have the ambiguity with respect to those satellites instead. So you are receiving the signals from not only one satellite, it is from number of the satellites. So as well as the ambiguity term is related with the satellite, so it also varying for every satellite. So you have N1, N2, N3, and N4 with respect to that receiver. We will see how the equations are written. Is that L1, L2, L3, L4, the prime observables, which we are writing here. This is the satellite clock offset. Again, you could see that this 4 cross 4 additional term is added because of these ambiguity term. So these are the additional parameters which we have to estimate to get a solution in the carrier phase measurements. So when we resolve the value of N for a particular receiver to get a solution, we call the process as ambiguity resolution. And you could see in the file which we are running for GAMIT, you have certain ambiguity resolved term which is written as that. So we'll see that part also. So in above equation, there are 8 unknowns, only 4 equation at a given epoch t with 4 satellites, which we for the code pseudo ranges process. So each additional epoch increases clock term unknown by 1. So what if we go for 3 epoch? I said 3 epoch, there will be 12 equation and 10 unknowns. So how the unknowns increased from this XYZ, N1, N2, N3, N4, and this, because of this, it is related to the epoch. So your receiver is not in a position, it is moving, it is static, so that's why there is no variation in this term with respect to the time, because your receiver we consider here as a static. This, unless you lost the lock, your value of n will not change. So obviously the term which will be increased as in terms of unknowns will be the clock offset. So every time you take the epoch, next epoch, so every epoch you have to calculate the estimate of receiver clock offset. So obviously those the 12 equations and 10 unknowns, you could see 1, 2, 3, 4 for epoch T1, 1, 2, 3, 4 for epoch T2, and 1, 2, 3, 4 for epoch 3. So that's how you become you have at least 12 observations, which we call it, and then similarly the matrix size will also increase, and this delta x, delta y, delta z term, as well as this clock offset. So you have to understand it. In order to solve it, how many epochs and how many satellites do you need to get a unique solution? We'll see that in this section, which we call it relationship amongst observable and parameters. That will be important, because when you see the Rhinex file and you try to use those Rhinex file for a particular session, you have to understand how many satellites are available and what type of different flexibility we have in our solution. So for point positioning, simpler equation is written Pijt plus the component of the satellite clock offset with respect to GPS time, and those on the right hand side are the so-called unknown parameters, which are embedded in those terms, which is the true geometric range as well as the receiver clock offset. So please remember, some of you may get difficulty, those who are not with the background of this with the GPS, is that this term, which we call it Nj cross Nt, should be greater than 3 plus Nt. What do we mean by this? This you must have little understanding about it. So Nj we refer to the number of satellite, Nt we refer it to number of epoch. So if you have 4 satellite and a single epoch for code pseudo ranges, please remember your code pseudo ranges, 4 satellite and a single epoch will give you 4 observables, isn't it? So the equation gets fairly straightforward, and 4 is equal to 4 here, because for every epoch you have this clock offset. So for the case of code pseudo ranges, this general phenomena which we said for the GPS, we initially have to have this 4 satellites. So this is for code pseudo ranges. So this again, the discussion is about how this epoch relationship with the respect of the number of satellites is relevant. So you could see here, what if you have just minimum number of satellites to make this eventually this doesn't become 0, is that Nj is equal to 2. So what will happen if you put Nj is equal to 2? Eventually you have to take the 3 epoch observation from those 2 satellites, isn't it? And as I said, in order to favor our satellite geometry, we don't prefer this to have a more number of observation or epoch observation from those minimum number of satellites. So we want our satellite geometry to be widely spread in the space, so that we'll don't get biased to the observation. So this Nj is equal to 4 is fairly straightforward solution, where for epoch 1 eventually gives the unique solution, and we can move with more number of epochs to get a redundancy in our the so-called least square solutions. So this again, for this equation for the code pseudo ranges, this is for the carrier phases, where you have this equation which is written for the carrier phases, and you could see because of this additional term here of the so-called ambiguity, you have Nj term which is coming up on the right hand side. However, in this case there is no Nj term. It is simply because you have ambiguity term with respect to the number of satellite is coming up additionally. So this Nj into Nt is related with nothing but with the so-called number of observations you are accumulating per epoch. So Nj into Nt is nothing but the number of satellite, number of epoch. So let's say you have 3 satellite, 4 satellite, single epoch becomes 4, 2 epoch becomes 8, 3 epochs becomes 12, which was the case in our carrier phase observations. So 3 plus Nj plus Nt, again will go for this relationship. The Nt should be greater than Nj plus 3, and what if we put the minimum number of Nj, so that 2, so for 2 satellites we need to have more epoch observation, and that's very straightforward because number of unknowns and the relationship with the number of observable. So here we'll increase the number of satellites for a particular epoch. So the moment you increase your satellite, so eventually the epoch observation gets also increased. So point positioning with carrier phases, we actually consider those certain number of unknown parameter to be fixed, and we fixed it, we introduced the so-called rank deficiency. So rank, you relate with your mathematics, that number of independent rows, isn't it? So this equation, when we introduce that for a particular epoch, I'm saying not only for all epochs, I'm saying for one epoch, you know what is the clock offset in your receiver. So let's say when you start your receiver, you know what is the clock offset with respect to the GPS time. So you enter those one epoch observation for the clock offset, and eventually your NT becomes NT minus 1. So because for a single epoch, we are introducing this. So that's how, again, new equation, NT should be greater than NJ plus 2, and because previously it was 3, because now 3 minus 1 becomes 2, so NJ plus 2 divided by NJ minus 1. So that's how you are, forcing us to get a solution with less number of satellite and less number of epoch. Okay, so this relative positioning, what we are doing in the case of relative positioning, or what we are doing during GAMIT, is that we are using those IGS stations around our location, and we are actually using the number of satellites which are common to them, so that this, instead of directly computing, suppose A is your base receiver, or you could say your IGS station, so instead of finding the position directly of your location, you are finding this vector. As we discussed in the first few lectures, instead you are now more interested on this baseline directly, rather than directly the position estimate of your position, the station. So it is the linear equation in this term vector domain, that xb is equal to xa plus that baseline component in 3 dimension, delta x, delta y, delta z, and this relative phenomena of where you are using those common satellites is nothing but you are actually eliminating those errors which are actually correlated with respect to those distances. So with the help of simultaneous observation, we are doing this. Subsequently, the application of this baseline vector, if you have an estimate, a very nice estimate of this baseline vector, as well as the error component also. So not only this baseline vector, which is 3 cross 1, we also have a 3 cross 3 matrices of the variance covariance matrix. So that will help us eventually to have a proper estimate of XP. So one can generally form this single, double and triple differences, which are actually the backbone of understanding the relative positioning. So we'll see what are those single, double and triple differences, and which one we actually prefer, and you will see that in your GAMIT, your manual also, which one differences is written in the first few pages. You will try to read those part also. So we are using the measurements of this baseline vector to estimate eventually our position, because we have a good estimate of XA. So differencing of observable, and here we are, see here the word relative comes. So whenever in general, if you follow the literature, so relative positioning comes with the differencing of observables but in phases, isn't it? So when you go for the differences of the observable, which are, you have carrier phases, you generally term this word relative positioning. So here in the single differencing, we are doing the differences of the carrier phases. So we'll see that. So single differences means you have either 2 satellite, 1 receiver, or 2 receiver, 1 satellite. So that eventually the terminology will also change accordingly. So between station 1 and B, you have 2 stations, common satellite, this part, or you have inter-satellite difference, and then you have 1 receiver. So eventually you could see, if you difference this with the measurement this, what is common at the satellite end will get cancelled out, and if you get difference of this with this, eventually the terms which are at the receiver end get cancelled out. So it is a beneficial at both ends. Obviously what we are doing here, you could see you have, because eventually we are not interested in this part, instead we are interested in this part, because we have 1 base and 1 rover. So the base and rover, if you are not familiar, base is those stations which are properly fixed with respect to your relative measurements. So base station you generally fix near to your site if you don't have access to others base station. So that has to have at least 24 hours data prior you take the observation from your rover, so that it has a fixed coordinate, or you assume that it has a fixed coordinate, so that you could consider as a base. And generally we make a terminology, those who have the base station which are we are using from past 10 to 12 years, we generally name it called CORS, which we call it continuously operating reference station. So we have to use those reference network also, and we'll see that part what we actually have, how to use those base network so called for the server positioning. So there is single difference between satellite station A and B for the, and please remember your baseline length, which is eventually the distance between your base and rover, is actually playing a role in your estimate. So please remember or be careful when you read the literature at how to make a session to be useful, that you have to understand this baseline is playing a role. Okay. So single difference, again straightforward equation, the phase measurement at station A with respect to jth satellite, the term obviously here with respect to the satellite clock offset, the right hand term is very clear. So you have one equation with respect to jth satellite, you have another equation for station B with respect to jth satellite, and what we are doing, we are differencing these two equations. So when you make differences, so some of you may not be aware about the concept of error propagation. So you have to also understand that when you are using two observable, eventually and you produce a third observable by using the combination of this, you are eventually prone to error propagation. So you have to also make sure that this should also come with the understanding when you are differencing two observations. So this phi ABJ is nothing but phi BJ minus phi J, simply differences. So the term notation is changes here. This becomes the combined so-called geometric range. This becomes combined ambiguity. This becomes the combined clock offset. Clock offset of A and B becomes this. So you are making a third observable by differencing these two. So eventually you are also making less number of equations. From the two equations you arrive at one equation. So obviously that will also create a problem while solving these solutions. Okay, so this relative quantities are nothing but the ambiguity, true geometric range, the clock offset, receiver clock offset, and the phase term. So this is the popular equation for single differences. You could see, and one very good book is available which we call it Hoffman, Bellenhoff by the GPS Theory and Practices. That's very good understanding of given about these all equations. You can follow that book also. So what will happen during this process? We actually forgot this concept. The single difference shows that single difference removes the satellite clock bias. So we don't have, if somehow those who are working with the GPS receiver and you have access to two stations but you don't understand the navigation message at all, what you will do, you eventually go to this kind of observation so that you don't have to estimate the clock offset of the satellite end. So eventually that removes this clock offset because you have a common satellite. Okay, so this is general summary. The summary is given by the book. Another book, those who don't want to read more mathematics, they can follow the book called by J.V. Sickle. It's a very good book for land surveyor, those who follow the understanding about session length, what do we mean by observable. So it's very good book with less mathematics. Okay, so single difference data. So obviously satellite clock eliminated, this ephemeris. So you could see what is eliminated and what is reduced. Why this, can anybody relate why this ionospheric, tropospheric terms are written as the reduced? Because it is written that it depends based on the baseline length. So that's why it is more important. When people say that we have taken the differences, so differences automatically gives you or help you only when you have a short distances between your base and rover. Okay, so noise, as I said, with the help of understanding of error propagation, it is increased by square root. You could relate with this. Okay, so another term which we call it double differencing, it is actually useful, and many people have seen also from the GAMIT manual that the prime observable are the double differences. So for 2 points A and B, similar to two satellites, and what we are doing, we are making the differences of two single difference. So when I say differences of two single difference, that means one pair is this and another pair is this. So that's also become the two single difference, and you differentiate these two single difference so that you get another third equation or fourth equation which is of double difference. So for point A and B, you have access to two satellite J and K. Differences of two single difference used to reduce satellite clock, orbit, localized atmospheric error, and you get rid of receiver clock also. So instead of solving a single carrier phase solution, you get a difference of the so-called two carrier phases measurement, and you eliminate these kind of errors. How the equation is written is, we will not discuss now again detail about the how this single difference equation is formed, but here the combined single difference equation with respect to J is combined single difference equation with respect to the kth satellite, and these are the two single difference. So again what we are doing, so if you go and look at this feeder, so how many initial starting observations were available to you is that one carrier phase measurement, another carrier phase measurement, another carrier phase measurement, and this. So you have at initially 4 initial measurement of carrier phases for those two receivers, and now you arrive at this. By differencing these two will become one single equation for double difference. So it is written very straightforward. DD can be constructed by taking difference of these single differences. Case 1 and 2, which because you cannot assume everything is straightforward, so same frequencies and different frequencies as well. So for the case of same frequency, the equation becomes very straightforward. This is your double difference equation. Now here you could see the clock offset terms is not. So this is a good observables to start with, because you don't have to deal with the clock offsets. So with the assumption that the observations are taken simultaneously and with the equal frequency. So the moment you go with the equal frequency, this Fj and Fk, either you work on L1 or on L2. So the similar equations can be written. These actually I was talking about that initially you have 4 prime observable of carrier phases, 1, 2, 3, 4, then you arrive at 2, then you arrive at 1. Similar to this, if you have double difference observables but for different frequencies. So one in case you have with L1, another is in case with you have L2. So similar, you could find that the multiplication with respect to those individual term will not be there. You have to consider both frequencies, and in order to do so, you could see this equation phi ABJK, which is double difference observable, this the combined geometric term, and this lambda k and lambda j, because here we are considering two different carriers altogether for double difference observables. So eventually we consider, and we by rearranging these two, will not get into the details. The rearranging terms, you could have this combined term with respect to one frequency. Instead of having lambda j, lambda k, you are dealing here with only lambda k, so that this becomes the case of what if you are doing with the second frequency only, and this becomes the bias. So above equation differs from DD equation by single difference bias BSD we call it, and it's nothing but the difference between these two wavelengths. And literature is available. If the wavelength difference for the two carriers correspond to this, which is typical for GLONASS carrier being separated by one carrier number, then the bias result. This is pure literature available. You could also find if you are interested. But what will happen in some summary? So satellite clock eliminated, receiver clock eliminated, ephemeris reduced because orbital error. You are taking consideration of both satellite at a time, and you are taking the differences. So receiver clock, where it is written as eliminated, ionospheric again reduced because these are depending on the satellite baseline length, and noise obviously increased by 2 because you are eventually going from 4 to another estimate. Another observable which we call a triple difference. The triple difference is that the epoch will increase from double difference. So double difference is available for single epoch. Now you have two double difference observable for two different epoch. So we are taking the difference of these two epoch, and assuming no cycle slip or loss of log has occurred, the equation is very straightforward. That this is the double difference equation for at epoch T1, double difference equation for T2, and now you have this very nice equation where you have get rid of this ambiguity term. So but eventually what is the trade-off is that noise is very large at this point. Okay, so this we are not going to the details of the correlation and or estimating those, how these the observables are correlated. You have single difference equations, you have double difference equation, you have triple difference equation. So variables are SD are uncorrelated. However, the variables of from DD and TD are correlated simply because the SD is computed from the prime carrier phases instead of TD and DD, where you have actually the single difference observable as their function. So we could call it SD is nothing but function of phi, but DD is eventually the function of SD, and TD is become function of double D, and eventually a function of single D. So again, this is again this equation which we have this for relationship between observables and the unknowns. So for single difference equation, this is I'm saying for single difference. So obviously you could see that this 3 plus Nj plus Nt, again Nj into Nt is for writing the understanding for the epoch with respect to the satellites available. You could see for a particular Nt should be greater than for 5 with the, if you take 1 it becomes 0, if you take 2, so Nt should be greater than 5. So for 2 satellite you have to take more than 5 epoch to get the final value of unknown. And why we are doing it? Because ultimately this term, which is the combined geometric term, is actually the delta x, delta y, delta z of those baseline vector are embedded in this. So we have to understand it, why we are going for these differences. Okay, so similar to, we are not going into detail, but we have to understand that why the Nj minus 1 is written. So I'll give you a moment to think why this Nj minus 1 is written here when we are writing the relationship among the two so-called observables and unknowns. So why Nj minus 1? Because from those two you are getting finally one double D observable. So that's why for Nj minus 1 becomes here. Similarly to this, you have a one combined ambiguity term or relative ambiguity term here. So Nt would become Nj plus 2, Nj minus 1, and similarly we are here taking the reference satellite as a common satellite, you could say, to make these double difference observable. So here let's say for example satellite are in your RINEX file is available as 6, 9, 11, 12, 16. So you are taking 6 as a common satellite and you are making these observables. Okay, so for triple difference, this is again, now here not only the satellites are reduced by 1, epoch is also reduced, because primarily you have 2 epoch and you have a final observable of 1 epoch. So that's why Nj minus 1 into Nt minus 1, both at the same time. So this again also straightforward, that you should be writing for Nt should be greater than Nj plus 2, J minus 1, and then you could see relate that for the minimum number of 2 satellite you have 4 number of satellites to be available. Okay, so what if you have kinematic observations? So it's very straightforward, don't need to worry. Only this change in this unknown term, for every epoch you are moving ahead. So let's say if you are in a vehicle and you want to take for the 10 epoch of data, so you need to have understanding this, you are actually working on 10 position for every epoch. So that's why this previously it was not there. Previously we are only taking as 3 because we are static mode. Now we are in kinematic mode. So apart from other, this term also related with the epoch. So for every epoch you have a position. So this is summary for code, for relative kinematic. So you can go through the summary. Okay. And those who have little understanding about the order, different order, they could see, although it is written as data type as 0 order, first order, second or third order, we also have design stages of GPS. So when we try to start the design process for establishing a network in our area or for a local study area, we have to go through the same design order, which we call it 0 order design, first order design, second order design, and third order design. So most popularly we have to follow the first order design, second order design, where we have to find the proper optimal geometry for our network that would serve our purpose, as well as instead of having all observation, can we actually find an estimate of which are the optimal observations which could eventually give the same kind of the precision in our final unknown. So that is also another way of looking at things. So zero order design, first order design, second order design, and third order design also could be have understanding about in a different sense. Okay, so summary with the working with the pseudo range measurement, CA code, PY code, you have real time positioning is possible. One receiver is sufficient for positioning and navigation, but eventually for a single receiver you have to consider, or you have to model, or the model should be available with you to consider the atmospheric error if you are not going for the relative one. So these are the say static positioning measurement strategies. The simple measurement strategies, the GPS antenna is fixed. Static positioning, observation may be for between 1 hour to 24 hours. So nowadays the RINEX file you are processing are 24 hours, so it's a fairly static mode. And issue is nothing but this is actually used for we call it application for crystal deformation. So those who are doing the crystal deformation studies or reading the papers, they will have the network which has certain data set of 24 hours. Similarly to this, the differential positioning, as I said, the differential positioning or the word DGPS comes from the fact that you are using the corrections to the pseudo ranges. Please remember, this DGPS word is nothing but is the differential GPS, but in this case you are taking the corrections which are estimated at the base end, but you are applying at the rover end. So corrections to the pseudo ranges becomes the concept of the DGPS. However, in the relative case you are working with the observables, prime observables of the carrier phases. So this is one difference of the nomenclature. However, nowadays people are using interchangeably. Okay, so consists of a rover and base, this DGPS, and obviously if you have to transmit the correction from base to rover, you need to have a medium through which you could transmit it. So generally radio modem links are available, you have and certain formats are also available, for which the popular one is RTCM format. You could read from the literature, and in that format you are getting the corrections from base to rover. So this is the so-called one simple example. It's again from the Sickle book. This is that you have a base station fairly stable, and then you have a rover in your study area. So for those common satellite, the base is actually estimating the pseudo range correction as well as range rate corrections, and it will be transmitted to the rover through a medium. So that will be applied at the rover end. So obviously the latency word comes also, that how much delay is that in applying correction at the rover end. So satellite orbits are valid everywhere, but propagation errors are only valid in the vicinity of the reference station. So if the distance between these two are less, the estimates at the rover will get more precise compared to the distance if more. Okay, so if you are doing the kinematic positioning, GPS antenna is mobile, the need for a reference station, so that for every time you get the corrections. So real time is also possible. Obviously the static mode is the most precise mode. Compared to static mode, you have the precision which is little degraded in other modes if you are going from kinematic to other. So this is the difference, is that we normally in the crystal deformation studies, we actually some of the surveyors are using the DGPS mode, and some are using the real time kinematic mode. So in the real time kinematic modes, you are getting the corrections directly in the real time. So is that position accuracy is plus minus 2 centimeters. So you have carrier phases, you have some same satellite constellation, and you are transmitting the correction to the rover. Okay, so we are coming to the GPS data combinations. What are those combinations, prime combinations, and what are the usefulness of those combinations? We have ionospheric free linear combination. So that what if you don't want, or you don't have access to the models which are available, so that how could you use those prime observables, which are nothing but the carrier phase measurements on L1 and L2, to get this free combination. So although it is very straightforward in terms of mathematics, I'll cover that in when we discuss the error budget, is that ionospheric is related with the frequency of the carrier. So because of which we could write these type of equations by multiplying first with this one, second with this one. This is only possible because ionospheric error is dependent on the frequency of the carrier. So when something is dependent on something, then we can only relate equation and we can use a difference of it. So linear combination is that L3 is a function of L1 and L2. So what we are doing, we are taking the measurements on L1, we are taking the measurements on L2, and we are using those to make a new combination, which we call it phase ionospheric free linear combination. Similar to this, we can write for chord ionospheric free linear combination, and you could see in this final term, in the previous equation or the first phase equation, we were not using this I term, which is related with the ionospheric error term. And here also another term which is I, when we discuss the mathematical model, but now we are discussing the ionospheric free linear combination, because it is the error is very prominent, and we have to understand this with the error of atmospheric error. So the free combinations are very useful. Similar to this, the advantages is that removal of the first order effects of ionosphere. Disadvantages, ambiguity is no longer an integer. This is a proper loss, is because you are multiplying n also with the multiplication term, which is f1 and f2, or f2 square or f2 square. So second is geometry free term. You get rid of this clock and the geometric term, which we call it range. So this is nothing but this phase geometry term, which we difference simply L1 minus L2. You will get this term. For chord geometry free combination, you will get P1 minus P2, you get this term. So obviously here in this case, we are not considering the geometry free ionospheric term. Please remember, we are considering here the geometry free ionospheric term. So the terms only the L1 ionospheric delay for 4 with respect to the L1 is written in this manner. Obviously the L4, the first two terms are constant in the above equation, because they are simply after resolution of the ambiguity. Hence derivation in the L4 represent entirely the variation in L1. Noise on L4 becomes obviously the error propagation if you go √2 of the L2, and geometric free chord pseudoranges therefore advanced by the obviously this is little interesting to understand that here the term changes, the notation over this sign changes. In the chord pseudoranges we started with this plus I, however by differencing it that becomes minus I. So when we say chord, in chord pseudoranges the ranges are delayed, and in phase we call it advances. So that's why the term says for that goes just change for the phase and chord. Okay, so wide lane combination, if you see that GAMIT processing the solution summary, you could see that wide lane ambiguity resolved percentage, narrow lane ambiguity resolved percentage. So that is another combination, but to maintain those integer nature of ambiguity. So with this you have phi1 minus phi2, and you arrive at a L5 solution, and you could see because of this the difference between two, the frequency get shorter and the wavelength becomes increases. So with this 86 centimeter kind of wavelength, you resolve the ambiguity, and there is a relationship between how to use those wide lane ambiguity resolved to get an estimate for individual ambiguities. So that you could use those estimate also to make a function of individual ambiguity. So let's say what we are doing is we are using these linear combinations to get a new effective wavelengths, and the similar combination can be performed for chord. The combinations is these are the characteristics of wide lane combinations, and similarly narrow lane combination, where you try to increase the frequency by effective wavelength is reduced. So again simply to P5, P6, and narrow lane pseudo ranges is delayed by in ionosphere, while the wide lane phase is advanced by the ionosphere. So similar by the term. And narrow lane has the same amount of ionospheric as WL does in meters. Also short wave length also makes it difficult to resolve the narrow lane ambiguities. Another MW linear combination, which is fairly straightforward. We are using L5, which is another linear combination of L1 and L2, and P6, which is another combination of P1 and P2. So we are developing this L7, and eliminates the effect of ionosphere, geometry, clock, and troposphere. And combination can be obtained by subtracting the chord narrow lane from phase line. With this we end this session, and any questions? Those who are working with one person who was working on the double differences, he actually wants to know about how can we start with this pseudo range observables, the double difference observables which we arrive at.
Sir, I want to know uh, if we have double differences, then how to approach using the double differences to get the baseline value.